Well, thank you so much for coming on such a sunny day. I thought I wouldn't get any audience at all on such a wonderful sunny day. But this is a wonderful opportunity for you and for me, because this book actually isn't out yet. So it's kind of exciting that you're getting a little advanced glimpse of what I've been up to for the last 3 years in writing this book. The catalyst for this book was partly the fact that I took over this new job from Richard Dawkins, the Professor for the Public Understanding of Science. And the title always makes me laugh somehow, because there's a kind of expectation with this professorship that maybe I know the whole of science, and that I'm here to explain it to the public. Actually, quite a few journalists seem to have this impression as well, because when I first got this job, I would get these phone calls from people. So I remember a journalist phoning me up. The Nobel Prizes for Medicine had just been announced, and this journalist phoned me up from one of the broadsheets. Said, yes, Nobel Prize for Medicine has just been announced for the discovery of telomeres. Could you tell me what a telomere is? Now, biology has never been my strong point. So I was like, oh my God, I've never even heard of a telomere. So I'm really embarrassed to admit. I mean, you can look me up on Wikipedia, but you can look a lot of things up on Wikipedia, actually. So I quickly went online, pulled up telomeres, read quickly through what a telomere was, and then confidently told this journalist that they're the pieces at the end of the DNA, which control how long a piece of DNA will last. And so I realized this is kind of crazy. There's no way I can be expected to know it all. But actually it began to make me think, is it possible at any point in history that science might know it all? Could we answer everything? Could we know everything? And so that was partly the sort of inspiration for this journey, was to see whether there are any problems in science that by their very nature we will never be able to solve. So actually the book's divided up into 7 edges of knowledge, which kind of took me on this journey outside of my own area of mathematics into different regions. And I'm going to take you through a few of these stories. But I think that kind of desire to know is absolutely basic. And it is extraordinary how much we have discovered, or the news stories coming out each week. I mean, I think since I took over this job, the sort of things we've discovered, we managed to land a kind of spaceship the size of a washing machine on the side of a comet. Absolutely extraordinary. We've got robots that we've programmed to develop their own language that we as humans can't understand. We have to interact with the robots to be able to understand that language. We've sequenced the DNA of a 50,000-year-old cave girl and repaired the pancreas using stem cells of a diabetic patient. I mean, this catalogue of things that we've achieved and the things we've discovered is extraordinary. And I think that basic desire to know is almost as basic as the desire to reproduce. And here's Aristotle, the beginning of metaphysics. He says, everyone by nature desires to know. In fact, I did a little research, and the word to know is actually one of only about 100 which have a universal translation across all languages. Not even the word eat is necessarily clearly translatable into each language. So an incredibly basic desire. But it's always dangerous at any point in history to declare you will never know something. And I've kept in mind on my journey throughout the last 3 years trying to find out those things that we cannot know. A few stories. One in particular is this guy Auguste Comte, who in the middle of the 19th century declared we shall never be able to study by any method the chemical composition of stars. Now, at the time, that seemed completely fair. I mean, how on earth are we ever going to visit a star to dig a bit out and actually find out what it's made of? But of course, a few decades later, we knew exactly what stars are made out of. Why? Because we don't necessarily have to go and visit the star. The star is visiting us every night. The light coming from the star is telling us what the star is made of. So it's always dangerous, and I'm sort of very clear that I'm not sure whether I've got any definitive answers here about things that you can absolutely say you can't know. But that was the journey, to try and understand whether maybe you can articulate that there are things that you will never know. Of course, the desire to know about the unknowable isn't restricted to science. I mean, there's a very famous example of a politician who got into quite a scrambled mess trying to describe his theory of knowledge. Here he goes, Donald Rumsfeld, trying to explain about the weapons of mass destruction in Iraq and whether they were there or not, declared there are known knowns. There are things that we know that we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns, the ones we don't know we don't know. Now, actually, Donald Rumsfeld got awarded the Foot in the Mouth award by the Plain English Speaking Society for this statement, but I actually think it's very unfair, because I think this is a wonderful statement about states of knowledge. The unknown unknowns, those black swan events. I can't tell you about the unknown unknowns, else they'd be known. I'm going to try and tell you about the known unknowns, whether we can know what those unknowns are. There's another category here that I think he missed, though, which I think is very interesting when it comes to a politician, which is, of course, the unknown knowns, which Slavoj Žižek actually pointed out was, those Freudian things that you actually know, but you don't deny that you know them, and but they come out and somehow, and I think probably those are the most relevant to a politician as the unknown knowns. So that was, so this journey to try and find the the known unknowns, I wanted to try and apply my mathematical mind to see whether I could articulate whether there were any questions in science. Another inspiration for this book actually came from the person that I took over this job as a Simone Professor for the Public Understanding of Science, because my predecessor was Richard Dawkins. Now, you of course know that Richard spent a lot of time not just talking about biology and evolution, but also about God. His God Delusion book was probably one of his most popular books. So I kind of braced myself when I took over this job for getting a lot of questions, not about telomeres, but about what my beliefs about religion were and God were. Now, I was quite keen to just create a sort of distance between me and Richard. We do very different things scientifically. And so I kind of prepared this response to journalists who would phone up and say, what are your religious beliefs? And I would tell them I'm a deeply religious man. My religion happens to be the Arsenal. I have faith every year, and it's been tested once again that next season we will win the Premiership. I go to my temple every Saturday or Sunday. This weekend it'll be Sunday. I sing songs to my idols and I worship them. And so I hoped that this would kind of bat away these questions about religion. But some of these journalists were very persistent. So I remember one instance on, it was a Sunday morning on BBC Northern Ireland Radio. It was a program about philosophy and religion. And I said, I'm quite happy to talk about philosophy and science and things like that, but I really don't want to talk about religion. Of course, as soon as we got on air, that went out the window. And he was like, so Marcus, do you believe in God? He wasn't from India, sorry. I will stop doing that. So he just kept on pressing me, and it became quite an aggressive interview, to the point that as a mathematician, you see, if you're asking me whether something exists, actually we spend a lot of time at the Maths Institute here proving things exist, maybe without being able to know what they look like, but we can prove that they exist, or often we prove that things don't exist. Andrew Wild, who this building is named after, proved that there aren't solutions to Fermat's equations. He had a way to prove these things do not exist. So I said, okay, I'm quite happy to engage in this if you give me a definition that I can start to engage my mathematical mind with. So he said, God, that's something which transcends human understanding. You've just played me out of the game. I mean, how can I engage with that? So it seemed to me, so I got very frustrated. Well, how can we start with the debate with that? But actually, that definition sort of stuck in my mind as quite an intriguing one. So as the years went on and I sort of decided to engage a little bit more, perhaps, with this kind of the bridge between science and religion, I began to think about that as a definition. What about the definition of God being the things that we cannot understand, the things that we cannot know, the things which transcend us? So can I apply my scientific mind to what that God would be like? And I talked to a philosopher in my college, in New College, Stephen Mulhall, just before I was doing an event with the chief rabbi, actually, he's got a wonderful book called Science and Religion, The Great Partnership. And he referred me to this guy, Herbert McCabe, who was a theologian here in Oxford, who actually a Marxist theologian. Get that? That's quite cool. But he's got quite a lot of crazy articles about Christian kind of traditions and things. But he had this one article which Stephen Mulhall referred me to, and in there he says, to assert the existence of God is to claim that there is an unanswered question about the universe. So I thought that's quite an interesting definition, and I sort of, through the book, I run with sort of just exploring a little bit about what sort of idea that is as a god. Herbert McCabe says, religion basically committed iconoclasm by giving this very abstract high concept too many properties it just didn't have. And of course, as kids, that's what we get introduced to, all the silly things, and then we sort of discard that. So I sort of wanted to have perhaps a more nuanced engagement with this question by defining something abstract like this. Now, there is this term, the God of the gaps, which you may have heard of, but that's actually used by religious people as a sort of as a kind of negative thing. A lot of religious people will say, no, you're meant to know God, you're meant to attempt to know God. So actually, the God of the gaps is something that they sort of use as a kind of negative statement. But I want to try and reclaim that maybe, and just explore through this book and a little bit with you now as we go through these attempts to find out what is it that could transcend our understanding forever. So as I said, the book is divided up into these 7 edges of knowledge, 7 areas that I've sort of explored, which go from trying to understand the nature of the universe, is it infinite, whether we can infinitely divide matter, what's going on inside our brain. So I'm going to take you on a little tour of a few of these to give you a sort of feel for what might be unknowable and whether we can know that sort of thing. I think one of the ultimate symbols of the unknowable is, in fact, the dice. A dice would not make a fun game if you could actually predict what this was going to do next. So the first edge that I explored is about the nature of the future. Can we predict the future? And in fact, mathematics at its heart is very much trying to do that. I'll call a mathematician a pattern searcher. What we do is look at patterns in the past and try and use those to extrapolate to understand patterns into the future. So how powerful is my language of mathematics in being able to predict what is going to happen next? So actually, each of the edges is accompanied by an object which kind of sparks my journey into the unknown. So the object for this particular edge is the casino dice. And this is, in fact, a casino dice that I picked up when I was in Vegas. And I was trying to use my maths to make a lot of money, and I lost so much money, but they let me keep the dice. That's nice of them. Now, it is a thing. It's a thing of beauty. I mean, you can come and look at it afterwards. It's because it has to be incredibly fair. It's really pretty much perfect cube. The edges are just beautifully sharp, and the paint's been sort of has the same density as the acetate. It's really. It is a thing of beauty, yet it also is something that I absolutely hate. Because I cannot, my desire to do mathematics was partly about wanting to know with 100% certainty that something was true. And here was this thing which, when I roll it, I just don't know what, I got a 1 that time, and I might be able to, I've got the equations for this thing, but, how can I tell what it's going to do next? So that was a kind of challenge. Actually, maybe if I work hard enough, I could know what this was going to do. And I guess the hero on my journey to try and use mathematics to be able to predict the future is Isaac Newton, because Isaac Newton came up with the laws of motion, the physical laws of motion, the idea of calculus. He showed us how the universe can be controlled. We can predict when an eclipse is going to happen. We were able to predict that Mercury was going to go across the sun just recently. And that's all thanks to this revolution that Newton started, which kind of revealed that the universe may be a kind of clockwork universe controlled by these equations. If you know how things are set up, you run the equations, you can know what's going to happen into the future. Well, if Newton is my hero, my nemesis in this whole desire to know the future is this guy here, Henri Poincaré, a French mathematician who at the beginning of the 20th century said, yeah, well, the universe may be controlled by equations. It may be that if you know the absolute startup of any system, you run the equations, you'll know exactly what's going to happen in the future. But he said, unfortunately, you're never going to have that complete knowledge of how a system is set up, because there's always a little bit of error. If you're measuring how the solar system is set up, then how can you be sure that you've got the 50th decimal place right? And what Poincaré showed is that just a very small change in maybe the 50th decimal place may cause a dramatically different outcome. Now, one of my favorite examples of chaos in motion, and this is an illustration that even something very simple can have a very difficult future to try and predict. So this is a pendulum. Now, a pendulum is generally something so simple and predictable, we use it to keep track of time. But this is a slightly different pendulum. So this is what I call a double pendulum. So it's jointed, so it's a little bit like a leg. So it's just two metal pieces here. So it's very simple geometric description, and the equations are equally quite simple. But being able to predict the behavior of this thing is almost impossible. So let's set this off. And you see, why are you laughing? Why? Because it's so hilariously funny that you can't predict it. It's just like, it's very interesting. It just always makes me laugh when and look, I'm going to try and, I had a little notch there. So the point is I'm going to try and repeat that behavior. I'm going to try and start it off in exactly the same starting position. So let's, wow, look, it's completely different behavior that time. And I think I've tightened it a little bit too fast because it's, let's do it a big one here. So this is my favorite desktop toy. I can play with this for absolutely hours. So, but it sort of illustrates that even very simple systems, you make a very small change to the conditions and it can go in a completely different direction. And this is the signature of something called chaos. Another of my favorite desktop toys is this one here. I use this to make all my decisions about life. So you can see it has different options. Ask a friend, try again, no way, definitely, maybe, yes. And what you do is, here's a little, I'll show you the little video of this. So this is one set up in a lab. You start this thing off and trying to predict this. So I'm going to ask it, shall I go to have a beer in the pub after this lecture? Let's see, oh gosh, it's kind of, oh, definitely. Oh, great, so that's good. Excellent, yeah. I think I've put it always says definitely when I ask it about the beer. It's really great. Thanks, yeah. But you can see from this that it, just if I run that again, trying to see, beforehand which magnet that's going to end up in. So there are three magnets here, and the thing is just being, pulled around. It's a bit like an asteroid flying around three planets, and which planet is it going to hit? Well, eventually goes for this one here. And here's three computer simulations I did where I actually just changed something like the 6th decimal place of the coordinate where the pendulum started. And you can see, so I've colored the pendulum, the magnets up now. So I've got blue magnet, a yellow magnet, and a red magnet. And just a very small change caused a completely different behavior, a different path, different planet that the asteroid hit. And here is a computer simulation which tells you, helps you to predict, maybe, where the pendulum is going to end up. So there are some regions which are very predictable. So if you're close to the yellow magnet, so the idea is if you start the pendulum off over a particular point, you look at the color under that point, and that will tell you where the pendulum is going to end up. So if I start near a yellow magnet, then the thing just wobbles about and goes back to the yellow magnet. But there are other regions which are a little bit further away. So here's a very large swathe of red. You start there, it'll swing out, but will then end up at the red magnet. So small changes are not going to cause any dramatic difference in where the magnet will end up. But I was starting that magnet in the top left-hand corner. And in this region, you have what's called a fractal. So this is a shape which has infinite complexity. So as I zoom in on it, it never simplifies. It never becomes a single color. So it means that however accurately I try and measure this thing, just a few more decimal places can kick it quite easily from going from the yellow to the red magnet. So this is saying that unless I have complete description of how the universe is set up, I cannot know the future in this region. Just a small change in a decimal place will cause a completely different outcome to happen. Now, I also was accompanied on my journey into these edges of knowledge by a few experts. I chose a lot of areas I'm not expert at all. It's very much was a learning curve for me, some of this. And in this chapter about chaos, I actually chose a a colleague of ours here in Oxford, this is Bob May, Lord May as he's now, and he actually discovered, I mean, this idea of chaos theory affects so much of what we're trying to predict about the future. The reason that I wasn't sure whether it was going to be a monsoon out there. I mean, yesterday we had monsoons kind of weather hitting us. Being able to predict the weather 5 days in advance is impossible because just a very small change in some of those measurements of the wind speed, temperature, can cause within 5 days things to go dramatically different. The planets too are very sensitive, but fortunately on a longer scale than 5 days. I mean, we're talking sort of 5 billion years. A very small change can actually cause the solar system to do something completely different. But Bob May has discovered that not only in these kind of physical systems, but also in biology as well. He's a mathematical biologist. He discovered that trying to keep track of population dynamics is also controlled by chaotic equations. So just a very small change, you put in one extra animal and the dynamics can be completely different. You can have the whole system collapsing, whilst without that animal you can have a very healthy pack of animals the next year. And in fact now he's working, he's a cross-party member in the House of Lords, and he spends a lot of time actually working on the banking crisis and trying to understand whether that was an example of a chaotic behavior. And sure enough, people in economics, there are regions like those yellow regions where things are very predictable, and then it can go into very strange, unpredictable regions. And he said this to me whilst we were talking. I went and had lunch with him at the House of Lords, and he said, not only in research, but in the everyday world of politics and economics, it would be better off if more people realized that simple systems do not necessarily possess simple dynamic properties. And I asked him, how are you getting on in trying to persuade your fellow kind of politicians about the importance of knowing about chaos theory? And he said, Marcus, there are just egos here. Nobody's interested in what I said. It's just they're all interested in their careers. So he was very down on that. But I think that is one of the important things when you're trying to do policy is knowing when you can be confident about what's going to happen next. I'm not saying that mathematics is completely useless. We've been able to land that spaceship on the side of a comet because of Newton's equations. But it's also important to know when you're in those regions, maybe in the top left-hand corner of that fractally picture, where now you can say you can't know. So it's almost as important to know when you can't know as to know when you can know, because then you can be conservative and hunker down and kind of avoid the mess that might emerge. So I came back to my dice and I was very interested, okay, well, what about this? Is this just chaotic? Or if I knew this to a certain amount of detail, could I actually predict what it was going to do next? I have the laws of motion which control how this falls, how it hits the table. And I actually discovered a recent piece of research done by 4 Hungarians which revealed that actually this is more predictable than I thought it was going to be. So what they've done is I had that picture with the 3 magnets, which I had 3 colors for. So now we've got 6 sides, and so we've got 6 colors to keep track of. So we can draw a picture of how we start off a dice and what that effect will have on the outcome, which colored face will it land on. And it turns out that if the table that you're throwing it on that dissipates quite a lot of energy, so it's sort of when it falls, the energy kind of gets sucked out of it, so like a carpet, for example, then actually the behavior of this is described by the picture in the top left-hand corner. So actually, if the energy is being dissipated, so if I throw this on the floor here, it doesn't bounce very much, and actually, it turns out that we don't have this fractal quality. There's swathes of yellow, swathes of green, swathes of blue, and so a small change is not going to change where that dice is going to land up. So here's a tip. Do you want to know which way it's going to land? What you need to look at is the bottom number, because it's more likely to land when you throw it like that on the bottom number. So in fact, I had a 1 on the bottom and it came up 1 there. So there you are, I'm quids in. But if you think about it, at the craps table in the, you've got a sort of felt on there. It's dissipating some sort of energy. But here, this is very hard, this table. So as you move through here, the rigidity of the table is increasing, and so it's losing less energy as you go through. So let's try and do that again, see whether... so down in here, we get a very fractal region. So now a very small change. So it landed a 4, whilst I had the 1 on the bottom that time. So it depends on the circumstances, but there are regions where I can know what this dice is going to do next. And actually, that's kind of one's thought is, I've sort of brought up on, the universe is controlled by equations, and if you know the complete setup, you should be able to know exactly what's going to happen next. Of course, we may not know the complete setup. That's what chaos theory is saying. A small change means that you might lose a lot of knowledge about what's happening next. But in fact, there's part of science which says, look, even if you know the complete setup of the universe, there are still certain circumstances where there's no way you're going to know what's going to happen next. And one of them is in the chapter that I explored next was trying to predict the behavior of a pot of uranium. So it's amazing what you can buy on the internet. So this pot of uranium, I ordered it over the internet, and I'm assured it's... I'm assured that it's completely safe, but the instructions say don't eat it. But this actually, at its heart, is the question of when this is going to radiate. At the side, it says that it's going to emit 984 counts of radiation. So if you have a Geiger counter, you get 984 counts per minute. So it's got some sort of estimate of what it's going to do, but that's only an approximate estimate. So it says, over a minute, on average, that's what you'll get. What it can't tell me is when it's going to emit an alpha particle, for example. And the extraordinary thing is, the current state of physics says that this is just how the universe is, that there is no mechanism, nothing that we can do which is going to tell us when this uranium is going to emit its next particle. That this, we say, is random, but that's actually just an expression of our lack of knowledge of the startup. This seems to be something which the physics says is genuinely random. And actually, the person sort of at the heart of trying to explain what this bit of uranium is doing, why it's emitting at particular points, is Heisenberg. This is a picture of Heisenberg. I'm trying to embrace and love Heisenberg, but he's another person I don't really like. And this equation, so you've probably heard of this thing, Heisenberg's uncertainty principle. Heisenberg's uncertainty principle almost embeds the idea that there are things you cannot know that you will never be able to know about a physical system. And its expression, it's not a kind of vague, wishy-washy thing about cats and Schrodinger and things like that. It's actually a very explicit mathematical formula and follows out of the mathematics. So these two terms here, delta x and delta p, this is about position and momentum. So basically, these two things are kind of paired up. And the more knowledge you get about the position of something, the less you know about the potential momentum. Momentum, remember, is how something is traveling. It involves the speed of the thing. And in fact, this is I've got to tell you one of my favorite jokes. So this is Heisenberg is storming down the Autobahn in Germany, and the police pull him over, and they get him out of the car, and they say, "Sir, do you know how fast you were going?" He says, "No, but I know exactly where I was." Now that's good. A good sign that you're all laughing, because if anyone who didn't laugh, and I now have to explain the joke a little bit, is that there's a trade-off here, and this is what this equation says. The more I know about the position of something, that's the delta x is controlling what the error is. So the more I know about it and the smaller the error, in order to make this equation true, the momentum has to increase. The uncertainty in the momentum has to increase. The knowledge I have of the momentum, I lose knowledge about it. And actually, it's perfectly summed up in some of these lovely experiments. Now, you might have experienced this thing or heard about this thing called the double slit experiment, where you send an electron through and it doesn't really decide. It seems to go through both slits at the same time. And actually, this thing about uncertainty is even revealed with just one single slit. So all I'm going to do is to take my uranium off in a very far distance, so that's going to be my particle gun. I'm going to have, say, an alpha particle shooting out of here, and I've got this, a large distance away, I've got a screen with a slit in it. And it means that if a particle passes through there, then there can be no momentum in the up-down direction. Because any momentum in the up-down direction would push it off and it would hit the screen and not go through. So if any particle that goes through that slit, I know has almost zero momentum in the vertical position. Because that's the only way. If it had any momentum, it would not go through that slit, because the distance I've made very large. But as soon as it goes through that slit, I also have now gained very tight knowledge about where that particle is, because it's gone through that slit. So I seem to have got the trade-off. I know exactly the momentum, and I know exactly the position of this thing. But as soon as I know the position, it causes a sudden uncertainty to occur in the momentum. So suddenly this thing gains momentum when it didn't have it before. And the uncertainty is expressed here. So this is actually experimental data where they took particles, they sent them through here, and the larger the smaller the slit, the more information I have about where that particle is, which means there must be a larger trade-off in the spread of momentum. And you can see this, the narrower slit is the bottom graph, and then suddenly the momentum is spread all over the place, so where the particle arrives on the screen could be in a wide range of possible values. But as I lose information about the position by widening the slit, the momentum comes back in again, and I have more information about the momentum. Now, this is absolutely extraordinary. It kind of says that I can't know these two things together. But actually, some physicists have started to interpret this and saying, actually, this is a mistake in language. That actually, these particles don't have a momentum and a position. We're so hooked on the way Newton thought about the world that we just think, yes, you've got this electron, it's got some position, it is somewhere, and it's got some momentum, and you use that to try and make predictions. But physicists now say, no, you shouldn't think of it like that. It's a wrong language. So often some of these kind of unknowns turn out to be just that we aren't able to use language properly. And so people now think that you should say, well, that electron doesn't have a position, an identifiable position, until you observe where it is. And so we have this thing now called a quantum wave, which actually describes the probability about where you'll find that electron, should you, or that particle, alpha particle, should you want to observe it. So you should think of this thing as not having a position. It's got a sort of probabilistic position spread out over space. The peaks of this wave function tell you it's more likely to be there. The troughs tell you it's less likely to be there. And this is all you can know. And you can't know where that electron is going to be. More dramatically, you can't know from the wave function, when you observe it, where it's going to be. It could be in any of these kind of peaks, or even in the troughs as well. And so quantum physics at the moment has at its heart this belief that it doesn't matter what you do, you will not be able to know and predict. And you can run the experiments over and over again, and you'll get different answers with the same setup, if you could ever start the thing in the same way. And actually, this is responsible for the uranium-emitting particles, because you know a lot about the momentum of the things inside the nucleus of this uranium, which causes an uncertainty in the position, such that at some points, suddenly the particle will say, hey, I seem to be outside the nucleus, I'm not inside it anymore, and it goes flying off. So this is actually, Heisenberg's uncertainty principle helps to understand why this thing is actually emitting particles. Now, there are some people who just believe this can't be how the universe is really behaving. You know, surely this just can't be random about what this is doing. And there must be some mechanism for deciding, okay, it might look probabilistic, the same as the dice. The best things we had to predict the dice is probability. But we know that there are laws of physics controlling what that dice is going to do. And one of those who really believed this just can't be the answer was Einstein. And Einstein had this famous quote, "Quantum mechanics is very impressive," and it certainly is. It's one of the most well-tested theories we have on the scientific books, with such accuracy that we know we're onto something. But an inner voice tells me that it is not yet the real thing. The theory produces a good deal, but hardly brings us closer to the secret of the old one. I am at all events convinced that he does not play dice. And I think maybe it's the mathematician in me, I'm still with Einstein with this, that, surely we will come to a point where we have a new theory, a new Einstein, that tells us something about the mechanism which is going on, which is controlling this. But we know that the mechanism is going to be really freaky. We know this thing called entanglement, which shows us that any mechanism, there can't be a sort of little internal clock in there, which is just saying, okay, now you're spitting out, now you're not, and whenever you look. This system, if it is there, we know must be sort of spread across the whole of the universe, which is controlling what this thing is doing. Now, I mentioned right at the beginning that part of this exploration was about this idea of God being the things that we cannot know. So here is something that apparently we are not able to know, when this thing is going to spit out a bit of its nucleus. So actually, the person I took on my journey to this edge of knowledge is a quantum physicist, but he's also a priest. So this is John Polkinghorne. He likes to call himself a vegetarian butcher because, how can somebody be a quantum physicist and also a priest at the same time? John Polkinghorne, he has incredibly good credentials. He's trained with Dirac in Cambridge, then went and trained with Feynman. He made great discoveries about quarks, and then halfway through his kind of scientific life, his life, he then decided that he wanted to be ordained. And so I was very intrigued to talk to him about how does he believe his God works in the world. I think that, there are a lot of religious scientists, and I must say, although said I believe in the arsenal, I am an atheist at heart, and I will declare that. But there are quite a lot of religious scientists, but they divide into two groups, and one are the deists, and one are the theists. The deists say, okay, look, I don't know where this universe came from. I don't know what started it all, what created it. But once it's been created, there's no, okay, I'm going to call that God, because I really don't know what it is which kicked this whole thing off. But after that, basically the laws of physics take over, and the whole thing is now something I can talk about. And so they don't think God acts in this world in any sort of meaningful way. But John Polkinghorne is a theist, and he really believes, whatever this thing God is, that it acts in the world. And so I was trying to press him, okay, well, you're a scientist, how is he acting in the world? Or how is this thing, it, acting in the world? And, we're thinking of it as the unknowns. So that's very interesting. So here we have an unknown, quantum physics. I don't know when this particle is going to emit or where I'm going to find a particle. Is that an unknown that can have influence in the world? Well, yes, it can. I mean, whether it has any sort of belief, whether there's any sort of meaning to what that action is. But so I was intrigued. Are you going to say maybe your God is using quantum physics so it can make a decision? Okay, I'm going to put the electron here and here, and that might actually have a dramatic effect on the universe because chaos says that small changes can have big effects. So I thought he was going to say yes, quantum physics, perfect place, my God, to act in the world. But he wasn't going to buy that at all. He said, no, because that really depends. All of these observations, all of these decisions about where the electron is going to be depend on an observation. It depends on interacting with the thing. And before that, it's just described by a wave function, a deterministic wave function. And actually, we're all part of a system. So surely what is an observation anyway? Surely we're all just part of some huge, great, big universal wave function. So he wasn't into using quantum physics as the way that his God was acting in the world. So I said, okay, well, how are you doing this? How is it doing it? And he actually went back to chaos theory, intriguingly. So his theory is that as humans, we can never know the setup of a system with complete accuracy. There will always be decimal places which we don't know about. And he believes that that's where a God could act and tinker with things and change things so it could be different as the thing evolves. Actually, Newton used to think this as well, and Leibniz, who was his great competitor over the calculus, just said that's totally ridiculous. Why on earth would he have to tinker? Why couldn't he just set the whole thing up and let it go running in the way that it was meant to at the beginning? Surely God is outside of time, so he knew exactly what was going to happen anyway. So it was a kind of intriguing journey talking to him about how would you use science to kind of marry up with your theistic beliefs in a God acting in the world. But the interesting thing as I went into this journey is that that reason that a lot of the scientific religious people who are deists, who say, okay, I don't know where all of this came from, let's call that creator, God, and then I'm just going to do science. And so that unknown, because it is, we don't know where it all came from. But actually, this Heisenberg uncertainty principle gives us a chance to actually see where this stuff came from. Because, okay, where did my pot of uranium come from? Well, I went on Amazon, so I bought it on Amazon. So that's its first source. And actually, there's amazing kind of reviews you can find on Amazon. So glad, 5 stars, so glad I don't have to buy this from the Libyans in the parking lot at the Mall anymore. There were some others complaining about the fact that the thing had disappeared, gone down by half. It's so good you're laughing and I don't have to explain about half-lives. Oh, that's so good. Anyway, so yeah, but if I trace this back, okay, yeah, probably, as I talked to somebody on Tuesday about this, and he said he was a miner, and he said, well, it's clear it came from a mine. Yeah. Yes. Okay. Yeah. But where did it come from before the mind? And you trace it back, and of course, it was made in a star. The most amazing thing, you know, how stars make all of these extraordinary atoms. But what about before that? So we trace it back. Where did all of this stuff come from? And it turns out that actually Heisenberg's uncertainty principle might be the equation which helps us to get something from nothing. This is one of the big unsolved questions. Why is there something rather than nothing? And actually, if you've got two things that measurements get paired up if it sort of matters what order I do it in. So measuring position and momentum, somehow it matters what order I do it, and they get combined in an uncertainty principle. But there's another uncertainty principle which combines energy and time. So this is expressed here. So any increase in the amount, if you want to narrow in on a little window of time, the energy within that window becomes less certain. So if you've got a region where there's nothing going on there, so you've got no energy, but actually if you decrease the window of time, that means that the energy uncertainty must increase, and so nothing might suddenly become a little bit of something, a little bit of error. And of course, Einstein said energy E equals mc squared. Energy is equivalent to mass. So you've got mass inside here. So as we look in a little window, actually we can suddenly get these what we call quantum fluctuations, where nothing can suddenly give rise to matter. So and this is actually, you may know what Stephen Hawking is famous for. He's famous for predicting that black holes, another place actually where we seem to lose information. If you go past the horizon of a black hole, inside we seem to not be able to know what is going on inside a black hole because information can't get out. One theory has it. But Hawking thinks there may be a way things can get out, and it's because of the uncertainty principle at the horizon is that although there's nothing there, every now and again this quantum fluctuation can cause a particle and an antiparticle to appear out of nothing. It's a bit like taking the equation 0 equals 1 minus 1. So you can have nothing and then suddenly get 1 and minus 1. And that antiparticle gets sucked into the black hole, makes it a little bit smaller, and the particle gets emitted out. So we believe in this thing, Hawking radiation. We haven't measured it yet, which is why he hasn't got a Nobel Prize yet. But when we do measure it, he will, because this is a way that black holes will actually kind of evaporate and may give back information. We think that there's something called the information paradox, that black holes may be somewhere where we lose information, but actually this leaking, according to this equation might be a way of us getting back information. But here is an equation which then gives us a way of getting uranium out of nothing. Now you might say, well, yeah, but that isn't really nothing because you've got space there. Space, just vacuum, isn't nothing. It's a three-dimensional space, and so that is something still. And as a mathematician, I certainly believe that. It is a something. So that isn't really nothing. So where did that something, where did that empty space, where did that empty geometry come from? But even now, as we push kind of one of the big mysteries is how to equate relativity and quantum physics, and the idea of quantum gravity and fluctuations in quantum gravity mean that even space itself might emerge as a fluctuation out of genuinely something which is nothing. So actually it might be that our desire for some creator is, well, actually the creator is just mathematics. Mathematics is outside of time. It's been there forever, will be there forever. And this is a way of just blowing something into those equations, and then you get something out of nothing. So, you know, often they say God is a mathematician. I would reverse that and say, no, mathematics is the God which started all of this. So that's a couple of the unknowns. So let me just give you a little guide through a couple more, and then I'll show you one of my. Let's see. One of the other ones is I dig down into my uranium and ask, you know, how far can you go? Can you infinitely divide uranium? Well, if you go inside it, that atom is made out of electrons and quarks. We think that's the bottom layer, but how do we know that? And we thought atoms with the bottom layer. So that one's, you know, we might keep on dividing space, although we think there's a little quantized space beyond which you can't divide anything. What about going out? Is the universe infinite? If it is, could we ever know that? So that's one of my other edges. Time, what about time itself? You know, we think time had a beginning, the Big Bang. But can we talk about what happened before the Big Bang? Now, I was brought up in this department on the kind of idea it doesn't make sense because you need time to say before. And so if there wasn't any time, you can't say before. And I thought, oh, yeah, that's really clever. Yeah, I like that. And they would always go, yeah, so what's north of the North Pole? And you go, yeah, I get that. There's kind of nothing there. Yeah. But actually, people are beginning to wonder that, no, maybe you can talk about time before the Big Bang. The weird thing is that time, is time infinite? Is it going to go on forever? Well, it turns out that it may also run out at the other end as well, which is kind of frightening. So time may, we know we're all finite, but what if the universe is finite? That's pretty frightening. And it turns out that everything's kind of decaying like these black holes, and all we'll be left with is photons and gravitons. And photons and gravitons have no sense of time. And so time will disappear. They won't be able to measure things. But actually, this seemed deeply depressing. So I went and talked to Roger Penrose, who is my sort of journeyman on this journey into time. And he's come up with a lovely, positive way of viewing this, that then you can rescale the universe because you've got lost a sense of time, and that will be the beginning of a new eon and a new Big Bang. So it was more hopeful. I love Roger. It's kind of, I love Roger as well because he changed his mind. He was one of these people I was brought up on who said, you can't talk about time before the Big Bang. And now he's changed his mind. I love that in a scientist. So I'm going to take you actually into a journey. I'll talk for another till 1:45 because I wasn't allowed to start until it, if that's okay. Because I do want to take you into this edge because this one really pushed me outside my comfort zone, which is the question about what's happening inside your head. It's called the hard problem of consciousness. You're all sitting there, and you're all most of you, doing a pretty good impression of a conscious being. I can see some of you sort of, which is fair enough. It's very sunny, but I do believe that most of you are, having a conscious experience. But is that conscious experience anything like the conscious experience I'm having? How can I ever know that you really are conscious, or whether maybe you've just sent an avatar down here, and you're doing such a good impression. And so actually, the object I took on my journey into the hard problem of consciousness is in fact, it's a chatbot app that I downloaded onto my smartphone. So I think there's a really interesting question: when will my smartphone become conscious? And could I ever know that? Maybe it already is. And it's perfectly encapsulated in this kind of Turing question. The problem of talking to a machine and determining at what point you say, no, okay, this thing is conscious. So I actually did a little experiment with this. It's called Cleverbot. You can download it for free, and you have a conversation with it, and you sort of try to think whether is it somebody on the other end typing these things in or not. So here's a little exercise for you. I did. I asked a few questions. I asked questions of Cleverbot, and I did this a bit earlier, and I asked some questions of my son. My son's doing physics in Bristol at the moment. He's 20 years old, just to give you some context. So I asked them both questions, and I want you to listen to the questions and think, can you work out which one is the machine and which one is my son? So we kicked off with, do you have a girlfriend? So response A came back, do you want me to have a girlfriend? Response B came back, mind your own business. Okay, so is that the machine? And the machine, of course, learns. It's an example of machine learning because every conversation you have with it is banked and becomes a conversation it will have with somebody else. Okay, the next one, what is your dream? So response A was, my dream is to become a famous poet. Response B, to make lots of money. Who was going to want to do that one? Yes, my son was born in the Thatcherite age, just to give you a hint. Question 3, are you conscious? Now, both of these responses are intriguing because they played on this idea of Descartes, I think, therefore I am. So response A was, if I wasn't, I don't think I... so it was quite convoluted, kind of. But this one is Descartes' response, which says, the only thing I can be certain of, and this goes as one of the topics of this book, is sort of, how can you know anything? And Descartes said, the only thing I can be sure of is of who I am. So it's the only thing I'm sure of is that I am conscious. So there you are, which one of those is a machine and which one is my son? And if we got the machine better, how could we ever know whether it was having a conscious world? Of course, some of you may be synesthetic. Anyone synesthetic here? Yes, there's a finger going up at the back there. What's you synesthetic with? Numbers and colours. My wife is a similarly synesthetic like this. And so they are having a genuinely different conscious experience because when they see a number, it gets coloured up. I did some wonderful work with a piece of Messiaen. Messiaen was synesthetic with sound and colour. So when he listened to his music, it was full of colour. So we know that people do have genuinely different responses, conscious experiences. But how can you tell? I mean, one of the things I do as a mathematician, very often if I'm trying to understand something, is to understand when something isn't that. It's a very good way to sort of flip the question. So an animal, take an animal. Which of these animals around us, which species are actually conscious. How many of these animals, if you stick them in front of the mirror, a cat, a dog, a rabbit, would know that what they're looking at is themselves? So here's the chimpanzee looking, and is he just admiring himself or doing a few kind of like funky moves? Now, here's a test that Gordon Gallup came up with, an animal behaviorist. He said, okay, well, if you put a mark on somebody's forehead, if you look in the mirror and you see something, oh, that's a bit weird, you put your hand up to your forehead. So he was interested, okay, what animals will have this similar response once you've got them used to what a mirror does? So here's the orangutan who's been marked, looking at himself in the mirror, so what is his response to suddenly seeing, oh, what's that weird thing I've got on my forehead? So that would be, if you put yourself in front of the mirror and you didn't know that somebody had put some yellow stuff on your forehead, you would immediately go like this. You wouldn't go like this on the mirror. So you can see, he's really pissed off that, why has this person put this great big yellow daub in front of it? So it turns out, how many animals pass this test? Very few. Humans do, chimpanzees do, and orangutans do. But gorillas do not. They don't have any response to this. It's very few species that pass this test. Now, it's a very crude test for consciousness, but it is a measure of them realizing that that is themselves. So what about children? If you've got a fetus, a fetus isn't conscious, but so here's a picture of me as a baby. I don't think I was conscious, didn't have a sense of self then. But what point in my evolution, as I grew older, did I suddenly start to pass that mirror self-recognition test and realize, yeah, I am a conscious being? There must have been a moment when my brain did something which changed, and then I had a sense of consciousness. It probably wasn't here. But with experiments that we've done, we've seen that actually there's a transitionary moment in the brain around 18 to 24 months. If you put a 16-month-old in front of the mirror with a little mark, generally they don't react. They perhaps do something to the mirror. But a 20-month-year-old will immediately do this. So something has happened in the brain that has changed, that has created this consciousness. And actually you can ask the same question of the universe. The universe at the Big Bang, was there any consciousness then? Well, so at what point did consciousness actually emerge? And actually, Julian James, a psychologist, he has an interesting theory that moment when we suddenly started hearing a voice in our heads must have been pretty frightening. And that might have been the spark for something like an idea of a God. Maybe that's what sparked off the thought there's something else going on inside here. Okay, so this idea of negatives, let me take you to this one. The time when we all lose consciousness every day, or rather every night, is when we sleep. So what happens in the brain every night that changes, that we could see maybe what a quality of the brain that makes us conscious. So here's an awake brain, and you do something called TMS. It's transcranial magnetic stimulation, where you switch on some neurons. So this is like a little computer gates. Those switching on some of those neurons cause a cascade across the brain and a feedback. The integrated network is actually talking to lots of other bits of the brain, feeding back to the original source of the stimulation. This is a sleeping brain stimulated in exactly the same area or with the same TMS in deep stage 4 sleep where you have no conscious experience. Everything is very localized. There's no communication going on across the brain. It's as if the tide has come up and all of the network has gone down. So there's now a belief that we can somehow measure the quality of a network. There's a guy, Giulio Tononi, who's come up with the way a network actually feeds back and forth between each other. The nature of those logic gates may have something to do with giving a network a feeling of what it's like to be itself. So Giulio Tononi has come up with this extraordinary equation, a coefficient of consciousness. Now, I've got to love this. What makes me is now an equation. And the varying quality of this equation as we go through the day and the night, or we go into a coma, that this can measure something about your conscious experience. To the extent, interestingly, that you can create a zombie. A zombie is something that has no conscious experience, but behaves exactly as a human would do. So here are two networks. They have 8 neurons. They're wired up in different ways. The input-output behavior of both of these networks is exactly the same. So if you interacted with it, you would not have any difference between the two. Yet one of them has a lot of feedback in it and has a high level of consciousness with this coefficient. But the one on the right has no feedback and it has a 0 consciousness according to this equation. And so this will be an example of a zombie network. Now, of course, I'm going to skip Wittgenstein, sorry. Actually, I will tell you about Christoph. Christoph is one of the people who got very interested in this equation, and I talked to him. He's my, I Skyped him, so I was never quite sure whether actually my conversation with an avatar or something, whether he was really there. But he got very frustrated with me trying to push him on whether we could ever answer this problem of consciousness. And eventually he said, what sort of research project is it, Marcus, where you throw up your hands and say, forget about it. I can't understand it ever. It's hopeless. That's defeatism. And I think we have a very schizophrenic relationship with this idea of the unknown. That, in one sense, the unknown is what drives us as scientists. The known things are great, but what we spend our life trying to understand are the things that we don't know. So in one way, the things we don't know are our lifeblood. But the things that will remain forever unknown, those are the kind of nemesis of the scientists. And so it is a belief. I think most of us kind of feel like, no, you have that arrogance that, yeah, we are a species that could know everything. And I think that's really what drives me when I throw the dice. Why do I keep on looking? It's my desire that I want to know how this is going to land. A 1. Thank you.